I normally like to start my lectures by talking about something I've seen recently. And if you're like me and you've been into the grocery store looking for something like toilet paper, all you've seen are empty shelves. And it got me thinking, what is it that makes toilet paper so hard to manufacture that they can't put enough on the shelves for people to wipe themselves with? So I got interested in the chemistry behind toilet paper, which is obviously an organic compound. And I thought that I would tell you about the manufacture of toilet paper, starting from trees to wood chips to cellulose fibers, and then we could talk about the chemical structure of cellulose. But that's not really the story here. The thing that got me interested is not the cellulose part, it's the stuff that they remove from the wood chips in order to leave behind this nice fluffy cellulose that makes soft paper. And so let's go ahead and talk about that, because what makes wood chips so resilient and tough is another compound, not cellulose, called lignin. And there's this chemical recipe, there's a set of chemical recipes they can use to cook at high temperature those wood chips in order to soften them up, in order to make this fibrous material made out of cellulose. So they're degrading the lignin, and there must be some interesting chemistry behind that. And let's go ahead and take a look at the chemistry behind that. I found two different processes for degrading this lignin. Let's take a look at this woody lignin molecule. You can see some semi-regular repeating patterns. Lignin is not a polymer. A polymer is a regular repeating pattern made up of small organic subunits, typically organic subunits. But this is non-regular. There's not exactly a repeating pattern, although there's repeating themes. And if you look closely at the benzene rings in here, you see that every benzene ring has an oxygen atom on one side of the ring. And then on the other side of the ring, there's a carbon atom that usually has an oxygen substituent, a benzylic oxygen. And that's what makes lignin cleavable under chemical conditions. You can cut this long stringy molecule up into tiny bits of string, of molecular string. Here's the chemistry behind the sulfite process for converting wood chips into fibrous material by degrading the lignin. And what they do is they use a combination of sodium sulfite and sulfuric acid. You've all heard of sulfuric acid. There's 4 bonds to sulfur. I'm not sure if you've heard of sodium sulfite or sulfite before. Sulfite has only 3 oxygen atoms on the sulfur, and the key behind sulfur here is there's a lone pair on sulfur that is nucleophilic. And so under acidic conditions, you're protonating and deprotonating every oxygen atom on the lignin molecule. But when you protonate this oxygen at the benzylic position of these benzene rings, the oxygen on the other side has a lone pair that can push out the protonated oxygen by resonance. And it leaves behind a benzylic carbocation that can now be attacked. This is a strongly stabilized, I didn't draw that resonance structure, but this benzylic carbocation is strongly stabilized by resonance from the oxygen atom on the other side of the ring. And when sulfite attacks, it makes a carbon-sulfur bond. And so not only do you cleave these lignin chains into smaller strings, but you also leave behind this anionic sulfonate group that makes it water soluble. And that allows the lignin molecules to float into the solution and leaves behind the cellulose pulp, which is what gets converted into paper. All right, that's the chemistry of degrading lignin using SN1 reactions. That's nothing more than an SN1 substitution process in disguise. All right, we've been talking about electrophilic aromatic substitution of benzene rings, and I told you that there were 5 reactions that you need to know for electrophilic aromatic substitution: how to form bonds between halogens like bromine and chlorine, form carbon-nitrogen bonds, carbon-carbon bonds, carbon-sulfur bonds. That's really the essence of chapter 18. And I gave you a mechanism, a 2-step mechanism for electrophilic aromatic substitution. And I said the only thing we were really going to change, was going to be the particular electrophiles that we're adding in those systems. So let's go ahead and talk about those electrophiles that we're adding and how it relates to the different recipes. So this first recipe that we're going to talk about is the one related to halogenation. And remember, I told you that if you add Br2, I want to see if the document camera is working here. Yeah. So if you add Br2 to a benzene ring, it replaces the H atom. And we normally don't draw those H atoms. I've done that for you here. So why would you care about making carbon-bromine bonds or carbon-chlorine bonds? What we're going to show you when you get into chapter 20, and I think I forgot to mention this, if you're using the 6th edition of the Gorzynski-Smith textbook, what we're really doing is chapter 16 in the 6th edition of Gorzynski-Smith. But in the 5th edition of the Gorzynski-Smith textbook, we're going to show you a secret reaction in chapter 20. And it's a reaction for converting this carbon-bromine bond. The bromine looks kind of like a leaving group, but it'll never act as a leaving group here. We're going to show you how to convert that into one of the most nucleophilic bonds in organic chemistry. Bonds to carbon magnesium and bonds to lithium, carbon-lithium bonds. Right? That is a super duper duper nucleophile. Let me just write that down here. Super nucleophile, more nucleophilic than anything else you have ever seen in the Chemistry 51 series. So that's going to be super valuable to put halogens on aromatic rings. And so I'm going to force you to wait until chapter 20 to learn that secret reagent that converts it into, I think you already know, the secret reagent is magnesium, but but it's going to be super important to put halogens on benzene rings because you can convert those into amazing nucleophiles. Okay, let's go ahead and talk about the mechanism for this electrophilic aromatic substitution. If we write out the bromine molecule, it's an electrophile. But if you put a super powerful Lewis acid in there, iron tribromide, that's a powerful Lewis acid. Lewis acids want to be attacked by things. And bromine is normally an electrophile. Alkenes can attack Br2, but in the presence of a powerful Lewis acid like FeBr3, the lone pairs on bromine can add to the iron atom of ferric bromide of FeBr3. And that's going to make this species where we now have an iron tugging on one of these bromine atoms. So we still have this single bond here. You're going to freak out over this structure. It's going to be like, what is this thing he's drawing there? This is going to freak you out, because you've never seen charges like this before. Sometimes I circle my charges if I think that it's not easy to see those charges. You don't have to circle your charges, your pluses and minuses. A lot of times I want to distinguish a plus charge from like reagent A plus reagent B. So sometimes I circle charges just because I think it might be easier for you to see them. But this whole thing right here with this iron attached to this bromine, this is now an amazing leaving group. I'm going to call it a super leaving group. Right? That makes it very, very easy to attack this bromine on the end, and then this whole thing will act as a leaving group. It is now so easy to attack this Br on the end that even a benzene ring double bond can attack. And so let's go ahead and do that. Let's go ahead and draw the mechanism for electrophilic aromatic substitution using this coordinated this amazing and powerful electrophile that we generate in solution. So we now have this bromine atom being tugged on by FeBr3. And again, I'm sure these charges are kind of going to freak you out. You've seen bromonium ions with positive charges on bromine before. When you brominate alkenes, you make a 3-membered ring intermediate that has 2 bonds to bromine. So that shouldn't be that unusual. And we're going to have the electrons in this benzene ring attack and give the electrons back to this Br+. Br does not like having that positive charge there. Now I told you yesterday, or sorry, on Monday, that I would advise you to draw the H you're going to substitute. Why not draw that in? Because you need that H on the next step. And if you don't draw it in and you forget to put that in on the next step, you're screwed. So I always draw that in on the first step, even though I don't actually use it for arrow pushing. So when we draw this next intermediate, this rhenium ion intermediate, it's going to have a bromine atom now. And our leaving group that's just kind of floating around there, let me draw the leaving group. Fe, I'm running out of room here because of this lettering here. It's this ferrate anion, and it might look weird to have that negative charge on iron. Don't worry about that. Now, according to my arrow pushing, I've left a carbocation here at this top carbon, and the benzene ring, this arenium ion, has lost aromaticity. It's not aromatic anymore. Boy, it really wants to be aromatic again. Anything can pull this proton off. I'm going to use the lone pairs on this Br. You may be tempted to use some part of the iron to pull off the protons. That's not the part that's electrophilic here. It's the lone pairs on the bromine atoms. All four of them are identical. That's a tetrahedral species. We're going to use that to pull the proton off and regenerate aromaticity. I'm making my arrow end at the carbon atom that's the carbocation. You could also make the arrow end in the middle of this double bond. Just be precise about which of those two you choose. Don't be wishy-washy about your arrow pushing. Be precise about that. So when you pull that proton off, it's really just a two-step mechanism, like that generic one I showed you. And so now we've generated an aryl bromide. We formed a benzene ring that's substituted by bromine. And as soon as I do that, I want to convert this into an organomagnesium reagent and use that as a nucleophile to attack carbonyls. That's really the essence of Chem 51C, is making carbon nucleophiles and attacking carbonyls. That's really what this chapter is about. And I've given you the first part of that process. Okay, so I said we're going to cover 5 recipes, right? We've just finished covering the mechanism for the first recipe. And the mechanism for halogenation with chlorine is you just replace all the Brs with Cls, and it's the same as the one I just showed you here. The mechanism isn't different for chlorination. It's the same, so I'm not going to bother to show you the mechanism for chlorination. All right, let's go and talk about the mechanism for nitration, adding nitro groups to benzene rings. This is how they make the explosive trinitrotoluene, or TNT. And, and it's going to be the same type of two-step mechanism that we talked about with that generic mechanism, and we're just changing up the electrophile. So here's our recipe. Recall our recipe is we use nitric acid, but it's not a strong enough acid. We need a powerful, the most powerful mineral acid that we have in our laboratories. That's sulfuric acid. And nobody really wants to have nitro groups on benzene rings. You're not going to find any drugs, at least as far as I know, that have nitro groups. They have problems with liver toxicity or something. So what everybody does once they put a nitro group on there is they immediately reduce that down into an amino group. We've got an entire chapter on amines coming up. That's chapter 25 in the 5th edition of the Smith textbook. So we're going to show you another secret recipe for taking a nitro group that nobody wants and converting that into an amino group that everybody wants. Anilines were the basis of the chemical industry. There were all these German dye companies that made dyes out of aniline. So BASF, the largest chemical company in the world, is Badische Aniline und Soda Fabrik. It's an aniline and soda factory. They made aniline dyes. Here's the secret recipe for reducing a nitro group down to an amino group, and that's hydrogen and catalytic palladium on carbon. It's the same conditions you use for hydrogenation of double bonds, except nitro groups reduce even faster than carbon-carbon double bonds. It's the best reaction ever. The only byproduct is water, which is easy to evaporate off under high vacuum. So again, nobody really wants nitro groups. They want amino groups, but this is the two-step process for doing that. Let's talk about the mechanism for nitration reaction. I mentioned to you that you need a powerful acid because nitric acid is just not powerful enough. And let's go ahead and start by drawing out the Lewis structure for nitric acid. Here's the Lewis structure for nitric acid. There it is. And I don't know about you, but if I try to think about what would happen if I treated this with a strong acid, even stronger than nitric acid, I feel like every single part of me wants to put a proton on the O-, and you have to resist that temptation. Right? You have to memorize this mechanism, because if you don't memorize it, you're going to start off by protonating the O- over here. And I'm just going to tell you that's happening in solution, but that's not part of the mechanism for the reaction. I'm going to check. There's just a few Q&As coming up. I want to make sure. I can't answer questions Okay, I can't answer. I just want to make sure that people aren't saying that like the sound is off or something like that. Okay, so here's what happens in the mechanism. And again, if you thought you were going to protonate the oxygen with the minus, that's happening. It's definitely happening, but it doesn't lead to nitration of a benzene ring. Most of the time you'll protonate O minus, take the proton off, protonate O minus, take the proton off. Every once in a while, you'll protonate this oxygen over here. And that's going to create a water leaving group. And it's reversible. You're protonating, I don't really need to draw the reversible arrow here, but you're protonating all the oxygens and then deprotonating. But every once in a while, when we protonate this OH, now we've created a great leaving group. And now we can use that O minus over here. Look at all those charges. Maybe that freaks you out. Sure freaks me out. Boy, I don't ever want to see you draw two atoms with positive charges next to each other ever again in this course. And so this is why you need sulfuric acid, the most powerful acid. Don't ever do this on any other structure ever again. Draw two atoms with positive charges. The second you touch this oxygen atom down here with a proton, it's going to get pushed out by the O minus lone pair. Let's go ahead and draw that. Push it out. There we go. And now we've generated our super duper electrophile. And we've generated a water leaving group. There's our water. And here's our key leaving group. It's something you've never seen before. I hope it freaks you out. It's like, what is that? I've never seen that before. Of course you haven't. This is a super secret, powerful electrophile called a nitronium ion. That's this thing right here. That's a nitronium ion. And that's the electrophile that is so powerful and so angry that it can add to benzene rings. So let's go ahead and do that. We're going to draw our standard two-step mechanism again. We'll start with a benzene ring. I'll draw my nitronium ion here. Boy, I just really want to attack that. And so let's go ahead and attack that nitronium ion. Now you can't tell where I'm going to form whether I'm going to form a bond to the top carbon or this carbon at 2 o'clock. You can't tell that yet until I draw the next structure. But I'm in this mechanism, I'm going to form a bond to this lower carbon here. So I'll just draw the H there. I told you, remember those H's. You need it in the next step. And if you forget to draw it, it's going to sink you when you're trying to remember the mechanism under stressful conditions on my exams. So you have to remember that H is so critical. Let me draw it there. We're going to need that. And let me go ahead and draw the nitro group here. We don't really need this Lewis structure for the nitro group anymore. But now this thing really wants to regain aromaticity. The benzene ring has lost aromaticity. You've got this uranium ion intermediate. Now anything with an oxygen atom in here can pull that proton off. It could be a bisulfate anion or some nitro species. We don't really care what the species is that's deprotonating, that's pulling that proton off. So I'm going to symbolize it in our mechanism by just drawing A minus. We're just trying to say that anything with a lone pair could serve as a conjugate base, whether it's neutral or charged, doesn't matter. We're just using A minus as a symbol, as a generic symbol to say that we don't care what that species is, but it's going to generate HA when it finishes protonating. So here we are on the mechanism, and we've regenerated aromaticity, and we now have that nitro group on there, just waiting to be reduced through hydrogenation conditions. And there's another resonance structure of this nitro group I could draw. I'm not going to draw both the resonance structures of that nitro group, but that's how you form carbon-nitrogen bonds to benzene rings. You use nitric acid and sulfuric acid, and it generates this powerful nitronium ion electrophile. Okay, so that's formation of carbon-nitrogen bonds. Let's go ahead and take a look now at the formation of carbon-sulfur bonds. I'm not doing this in exactly the same order that I showed them when I showed you those 5 recipes, because I showed you the 5 recipes where the top 3 of those recipes were the most common ones. Formation of carbon-sulfur bonds is not quite as common nowadays. So it's not the most useful reaction, but it's in the textbook, it comes next in section 18.4, or if chapter 16 if you're using the 6th edition. Okay, so the reagent that we use here is sulfur trioxide. And if you recall, I told you have to add an acid catalyst to this reaction. Sulfuric acid, again, sulfuric acid. And you can buy bottles of sulfuric acid saturated with sulfur trioxide gas. So if you want to do a sulfation reaction, you don't have to actually get 2 separate reagents. I think the reason why the book covers this is because one of the first antibiotics that was synthesized using organic synthesis was a class of drugs called sulfa drugs in the 1930s. Nobody uses those anymore. We should have stopped teaching this in the 1930s, but whoever wrote the textbook is a little bit out of date, but we're just going to follow along here. This is the way you make tosyl chloride. You take toluene and you do this sulfur trioxide reaction, and then there's a reaction to convert that OH into a chloride to make the reagent tosyl chloride. And you used tosyl chloride, I think back in chapter 9 or 10 to make tosylate leaving groups. Okay, let's go ahead and walk through the mechanism for this sulfation reaction. So we're going to start off with our reagent here. Let me go ahead and draw out sulfur trioxide. It's a planar molecule that's trigonal. It's got 3 oxygen atoms attached, all with double bonds. And in the presence of a powerful acid like sulfuric acid, I'm not going to draw the structure of sulfuric acid. It's irrelevant. I'm just going to use the symbol HA. That way we don't have to worry about whether it's H attached to sulfate or H attached to an rhenium ion. We don't even care. Just some super powerful species under these strongly acidic conditions is going to protonate the sulfur trioxide and make it really electrophilic. So we'll protonate the oxygen atoms there and release that conjugate base A-, which will then be floating around. And so this is our powerful electrophile that's going to add to benzene rings. Now, there's a couple of different ways I can depict this structure here. I can draw it with 3 bonds to oxygen. That's called an oxonium ion when you have 3 bonds to oxygen. And there's another resonance structure I could draw. They're both of these resonance structures are fine. If I draw this other resonance structure, I think it will be more obvious to you, right? If I draw another resonance structure like this, it may be more obvious to you why you attack the sulfur atom. All right, you don't attack the thing with the positive charge, you attack the sulfur atom. That's the electrophile. And I could have gone straight there if I simply made my arrow start with the SO double bond. It would have led me directly to that resonance structure. So let's go ahead and draw this 2-step mechanism for electrophilic aromatic substitution using protonated sulfur trioxide. It doesn't have this nice, neat name like a nitronium ion. It's got this kind of clunky name, protonated sulfur trioxide. Boy, I wish I had drawn the other resonance structure. Let me do that. Sorry. Just to make it look like the other mechanisms I drew. I just wanted to draw this resonance structure. And let me draw that protonated sulfur trioxide molecule. And we'll make this benzene ring attack. Let me draw the CH bond that's there. Right? I'm not going to use the CH bond as the nucleophile. I just want to see that it's there so I don't forget it in the next step. That could have been a better plus charge, so let me just decorate that to look a little more like a plus. And so now we generate that rhenium ion intermediate that we talked about. Here's the rhenium ion. Boy, it has now lost aromaticity. So angry. It just wants to get back aromaticity. It's not aromatic. And anything in there can pull that proton off. I'm going to symbolize the thing that pulls off the proton using a symbol for conjugate base. That's A-. Again, it could be a lone pair on sulfur trioxide that's pulling it off. It could be I don't know, some other, anything with an oxygen atom could pull off this H. We don't care. We're just going to symbolize that using a generic symbol A- when we draw mechanisms. If I ask you to do a synthesis problem, and I say, give me the reagents to convert benzene into, I don't know, some drug, then I want to see chemical reagents. But if I ask you for an arrow pushing mechanism, then you can use symbols like HA for acids or B for bases. Now we pull off that proton and we regenerate aromaticity. And that's the mechanism for electrophilic aromatic substitution to create sulfonic acids, arene, benzene sulfonic acid derivatives. So it's following that sort of pattern of you generate a powerful electrophile and then the double bonds of the benzene ring attack that powerful electrophile. Okay, we need to know how to make carbon-carbon bonds directly using electrophilic aromatic substitution. So let's go ahead and talk about that. So I showed you a recipe where you take this species called an acid chloride, and I think it's possible that the book may be using the more modern nomenclature called an acyl. It's 2 words. Sorry, I didn't leave a space there. An acyl chloride. But I think old folks like me use the word acid chloride. I'm not sure, they may be calling it an acyl chloride in the book. The bottom line is these types of species with a carbonyl that have chlorine attached to them are super useful, super useful. Anytime you want to make a bond to a carbonyl, if you've got an acid chloride, you can make carbon-oxygen bonds, carbon-nitrogen bonds, carbon anything. These acyl chlorides are so useful. And this is your first reaction where you get to see those in play. It's this reaction called a Friedel-Crafts acylation reaction. So when I hear the word Friedel-Crafts, what you're normally thinking is that's for forming carbon-carbon bonds to benzene rings, doing electrophilic aromatic substitution. Let's go ahead and draw out the mechanism. We've got a Lewis acid here that's even more powerful than FeCl3 or FeBr3. Man, aluminum just wants oxygens to attack it. Aluminum is so electrophilic. So here's our acyl chloride. I feel like based on everything I know in organic chemistry, I want these oxygen lone pairs to form bonds to aluminum. That's happening. The lone pairs on oxygen are attacking the aluminum and then they're coming off. They're attacking aluminum and then the aluminum pops off. But every once in a while, it's the electrons, it's the lone pair on chlorine that attacks the aluminum. And I'm missing the L from my aluminum. Hope you could, that doesn't look very well. That's aluminum trichloride. That's the worst aluminum elemental symbol ever. But you get the idea. So most of the time, it's lone pairs on oxygen attacking, coming off, oxygen attacking. But every once in a while, you do this. And oh my gosh, you've set this thing up to pull off the chloride. So now you generate another one of these weird looking intermediates that's going to make you uncomfortable, right? At this point in time, you're not used to putting positive charges on chlorine. You're used to making chloride anions, probably. But now we're putting a positive charge on chlorine. It hates that. And you've got this, don't forget, if we put another bond to aluminum, we have to give that a negative charge. If you have aluminum with a negative charge, you don't call it an aluminum, you call it an aluminate. The species is called an aluminate. If you put a negative charge on iron, it's called a ferrate. Put a negative charge on copper, it's called a cuprate. I would refer to that as aluminate. But when I see a positive charge on chlorine, I would call that a chloronium species, 2 bonds to chlorine. Well, that thing wants to act as a leaving group. This whole thing now should be kind of reminiscent of the iron thing. That's a great leaving group. And that's convenient because there's a lone pair on the opposite side of this carbonyl that's ready to attack from the back side and push out. That whole leaving group comes out. There we go. It just comes in right from the back side, the way you draw SN2 reactions. That's not SN2, but kind of reminiscent in some way. And that generates the key species here. It generates, I'm going to draw the carbon atom now, and now I'm going to draw 3 bonds to oxygen. Kind of looks like carbon monoxide. There's 3 bonds to oxygen in carbon monoxide, CO. This is kind of going to look freaky to you, this species. It's called an acylium ion. This species that I've got the name right above here. This is called an acylium ion. That's the electrophile that's super powerful. And here's the byproduct that you generate when the aluminum pulls that chloride right off. It's a tetrachloroaluminate counterion. That's the species that's in there. But this acylium ion is super electrophilic. And it may look weird to you, but it's actually more stable than a T-butyl carbocation, because every second row atom, there's a lone pair on that oxygen, has 8 electrons. Oxygen has 8 electrons. Carbon has 8 electrons. So it's a powerful electrophile, but don't get too freaked out over that. It's not that crazy. But boy, is it reactive. And so if you have an unsubstituted benzene ring, you can attack those acylium ions. So let me draw that acylium ion just hovering over here, ready to be attacked. There we go. We'll make this, don't attack the oxygen. I feel like you're so used to attacking carbocations, where the carbon only has 6 electrons in the carbocation, that maybe you think you should always attack atoms that have positive charges, and you need to just get that out of your mind. Carbocations are reactive not because of the positive charge. They're reactive because they only have 6 electrons. So don't attack this oxygen atom because it has a positive charge. It's already got 8 electrons. Attack this carbon atom over here, and then we'll give the electrons to oxygen. We'll break that pi bond. That's the way to draw that mechanism. I'm going to draw that H atom here just so I don't forget that it's there. I'm running out of room here, so I'll try to make this a little lower on the page. And so we generate this rhenium ion intermediate. Now has a new carbon-carbon bond that wasn't there before. And there we go. And R can be methyl, ethyl, isopropyl, phenyl. It can't be oxygen or nitrogen. We don't have acid acyl chloride reagents like that. But it can be any alkyl or aryl group on there. Okay, so we generate this rhenium ion intermediate, and I think you know what's going to happen next. We've now done this several times. We're going to deprotonate that rhenium ion and get back aromaticity. So I'm going to symbolize the species that pulls off that proton by drawing this symbol for a conjugate base. We don't care what that species is. There's all kinds of things in there that have lone pairs. There's oxygen atoms with lone pairs, chlorine atoms with lone pairs, tetrachloroaluminate anions with lone pairs. That's probably the most basic species in there. And any of those species could pull this proton off. And we don't care which species it is. We just want to symbolize that with an A-. And so that regenerates aromaticity. And now we've got a carbon-carbon bond attached to the benzene ring. And as soon as I see that carbonyl, I want to attack that carbonyl. I want to attack it with things. I want to attack that carbonyl to make carbon-carbon bonds down here. I want to attack that carbonyl to make imine derivatives, all kinds of species. That's what Chem 51C is about. Chem 51C is about attacking carbonyls. A lot of Chem 51C is about making carbon-carbon bonds by attacking carbonyls. But it's super useful to be able to make benzene rings attached to carbonyls. That's because we're going to make we'll add even more nucleophiles to that carbonyl derivative. Okay, let's go ahead and talk about, I think, our 5th type of electrophilic aromatic substitution reaction. And that's a Friedel-Crafts, not an acylation, but a Friedel-Crafts alkylation. And the recipe is going to look stunningly similar to that Friedel-Crafts acylation reaction. Instead of having an acyl chloride, we just have an alkyl chloride. This looks like something you might have made using an SN2 or SN1 reaction or some version of that. So I already told you in these reactions, these do not work well unless you use an excess of the benzene. You have to use the benzene as a solvent, which is fine if you're only doing reactions with benzene because benzene is a cheap solvent, but anything other than benzene, it's not really that good to waste all the benzene because you throw the extra benzene away. So you don't keep the extra benzene that doesn't react. So You can also do this with alkyl bromides if you wanted to, but you still use the same catalyst. So we use the same catalyst, aluminum trichloride. Remember how aluminum trichloride tugged off the chlorine atom from that acyl chloride in the Friedel-Crafts acylation? It's going to do the same thing over here. So let's go ahead and get started with the mechanism. We start off by making our electrophile. We take our alkyl chloride, and it's got lone pairs on there. And we've got that aluminum that just loves lone pairs. And now we're going to make the chlorine lone pairs attack the aluminum. There we go. It's going to turn that chlorine into a great leaving group. Whoops, I keep forgetting to draw that aluminum L in the aluminum symbol. And with 2 bonds to chlorine, you better put a positive charge on there. That's called a chloronium ion when you have 2 bonds to chlorine. And if we just put an extra bond to aluminum and it didn't have a 4th bond before, we now have to give it a negative charge. So notice how the charges balance out. There was a net charge of 0 in the starting materials. There better be a net charge of 0 in the next set of intermediates, because there's this principle called conservation of charge when you do elementary reaction steps. So now that creates this super powerful leaving group. So remember how this was a leaving group before that's powerful? I'll just put I can't fit the word powerful in there, so I'll just say leaving group, exclamation point. And you know that's a powerful leaving group. And so now that aluminum just tugs that chlorine right off of there. Let's give the electrons back to chlorine. And we make that tetrachloroaluminate counterion. You know, it bothers me when I draw carbocations. I always feel I'm not going to draw all the bonds. I'll just draw it like this. It bothers me when I draw carbocations if I can't see everything attached to that carbon atom. I feel this compulsion to want to draw the H there, because I just like to keep my eyes on carbocations. I can't resist it. I have to draw that H. There we go. It's not a tertiary carbocation. That's much more stable. It's a secondary carbocation. Extremely reactive. Those are hard to generate. So you haven't seen this recipe for generating secondary carbocations before. Okay, let's go ahead and draw the mechanism, the 2-step mechanism for electrophilic aromatic substitution. Here's our carbocation. And I'm not going to draw, I feel like I want to draw the H, I just don't want to confuse things. And here's our mechanism. We take the double bond in the benzene ring and we attack the carbocation. That's our electrophile here. And it forms a carbon-carbon bond. Like I said before, I'm going to draw the H. You don't have to draw that H in this first step, but I've just seen so many people miss the mechanism for electrophilic aromatic substitution because they couldn't remember that in this step there was an H there, and so people who don't remember there's an H tend to want to attack the carbocation. And I'm just trying to save you some headache there. We have to focus on that H. This system really wants to get back aromaticity. Again, we don't care, something's going to pull that proton off, and we don't really care what that species is. It's something with a lone pair, probably the tetrachloroaluminate, with a lone pair on there that's pulling it off. We don't care though. We just care that something's pulling it off and regenerating that 3rd bond of the benzene ring in order to regenerate aromaticity. And this is called a Friedel-Crafts alkylation reaction. So you'd think that alkyl groups are so simple and so common, you'd think that this would be the most common of the electrophilic aromatic substitution reactions. It's not the most common, or it's not the most useful. It's one of the least useful ones. We'll find out more about that later. Okay, we've got 5 different recipes for electrophilic aromatic substitution. We have halogenation of benzene rings with bromine and chlorine. Then we have nitration of benzene rings to form carbon-nitrogen bonds with nitric acid and sulfuric acid. We have sulfation of benzene rings with SO3, sulfur trioxide, and sulfuric acid. And then finally we have this Friedel-Crafts, this set of Friedel-Crafts reactions, Friedel-Crafts acylation and Friedel-Crafts alkylation, both with aluminum trichloride. There's another version of Friedel-Crafts alkylation. You can see that all this aluminum trichloride and alkyl chloride business It's really there just to generate a carbocation. And what happens if you generate carbocations in other ways? Turns out they can still do Friedel-Crafts. They can still do alkylation of benzene rings. Let me give you an example. So sometime in chapter 10, you learned that you can hydrate, you can add HCl to CC double bonds, you can add water to CC double bonds, but it always starts with protonation of the double bond. And so we can use the same conditions that we use to generate carbocations in chapter 10, and those carbocations will add to benzene rings. Let's go ahead and take a look at how that works here. So I shouldn't have to tell you that you can protonate CC double bonds. If you don't remember that, go back to chapter 10. It's full of reactions where the mechanism involves an initial protonation of a CC double bond. I'm going to draw out the mechanism here, but I'm going to depict the acid just as HA symbolically for the arrow pushing mechanism. That's the sulfuric acid, but we don't care what species is protonating that. So what we want to do is, it's much easier to protonate alkenes than benzene rings. So let's go ahead and start by doing that. We'll go ahead and protonate that alkene. And we want to protonate it on the carbon that leaves behind the most stable carbocation. So that means put the proton on the top carbon and leave behind a tertiary carbocation. Don't protonate the bottom carbon. That would leave a primary carbocation. That's crazy. No way that's going to happen. We protonate the top carbon because we want to generate the more stable of the two possible carbocations. There's our carbocation. I'm going to draw the positive charge down here because I want to leave room for me to attack that. And here we are. And now we're just going to do a regular electrophilic aromatic substitution, just like the 5 other ones we did. You know what the benzene ring is going to do. The benzene ring is going to attack. Don't attack the charge. If you drew a plus charge here, don't make sure you never attack charges. Charges don't form bonds. Electrons form bonds by bonding to atoms. So, and I'm not going to draw the rest of the mechanism, right? We've just done this 5 times. You generate an rhenium ion, and then there's a proton here, and then you pull the proton off in the second step. And I'll just put, I don't know what to put here, but you know the drill. It's a 2-step mechanism after you generate the electrophile. Okay, carbocations are tricky. Man, they are so tricky. So I want you to be cautious. And the book loves to just trick you every way possible by giving you a crappy reaction and then seeing if you can guess how badly the reaction goes. Let me show you an example of how carbocations can lead to tricky rearrangements. So if you take a primary alkyl chloride and try to make a primary carbocation so you can do Friedel-Crafts, it's not going to work. So right, if we come over here and we add aluminum trichloride, and then it pulls the chlorine atom off, and it makes let me go ahead and put the H down here. There was an H here at this position. So if we try to do our Friedel-Crafts trick and try to make a primary carbocation, that thing is not going to just sit there. There's no way that that's going to last long enough for a benzene ring to come and attack. Long before any benzene ring comes anywhere near this primary carbocation, something else is going to happen. What will happen is there's going to be a virtually instantaneous, let me try to use my black pen again, a virtually instantaneous 1-2 shift, a 1-2 hydride shift. Those, you can't stop those. If it's possible to do a hydride shift and go from a primary to a tertiary carbocation, you can't stop that from happening, right? This is what's going to happen. Instantaneous, fast. And so the Friedel-Crafts reaction that you were hoping to do with a primary carbocation is not going to work. Those are going to do rearrangements, 1-2 shifts, hydride shifts if they're possible. If they're not possible, sometimes they do 1-2 alkyl shifts. But you know, if you want to make bonds to primary carbocations, you can just forget about that. So now when a benzene ring comes in and attacks that, right, we've got 3 carbons attached here. There's that carbon atom. I'll put a little ball there so you can see it. There's 1, 2, 3 carbon atoms. And the benzene ring, if you do Friedel-Crafts alkylation reactions. I'll just write Friedel-Crafts, you know, or maybe I should write electrophilic aromatic substitution. Instead of, usually I think of aluminum trichloride when I hear Friedel-Crafts. But again, you start thinking you're going to make a bond to a primary carbocation, it's not going to happen. You're going to get rearrangements. And I don't know why the book loves to ask you this so they can try to trip you up to not recognizing there was a rearrangement. And I'm just telling you, you've got to keep from being tripped up on that. If I wrote the book, I wouldn't even include that reaction. I'd say, why don't we focus on good reactions? Don't do tricky stuff. But I think most sections of organic chemistry, most professors love to try to trick their students in some way. I don't know why. Okay, we've got I'm going to give a heads up here about what's coming up in our next lecture. I'm not ready to cover all of this right now during our lecture today. But what we have to immediately think about is that you want to do electrophilic aromatic substitution, not just on unsubstituted benzene. That's boring, right? This chapter would be about 6 pages long if every reaction was done with benzene. What happens is you start with benzene rings that already have a substituent, and then we have to worry about, okay, if we do electrophilic aromatic substitution on this, where does the second substituent go? That's what creates most of the work in this chapter, is figuring out, if you've already got a substituent on your benzene ring, what position do you add to when you add the second substituent? And we have names for these positions. Like if we have an alkyl, if we have a substituent already on a benzene ring, these 2 positions that are next door, we refer to those as the ortho positions. Ortho. Ortho. These 2 positions that are down 2 atoms away, we call those the meta positions of a benzene ring. Meta. And then finally, this position on the opposite side of the original substituent, we call that the para position. And it's just a way to describe a relationship, either next door, 2 atoms away, or on the opposite side means para. So when you look at these possible products, they don't all form in equal amounts. We'll talk about that when we come back. We call this product the ortho substituted product, the ortho product. We call this product down here the meta substituted product. And we call this relationship down below para. It has a para relationship. That's the para substituted products. We have this new language that you need to learn about. And I'm going to refer to things as ortho, meta, and para all the time, starting right now. So become familiar with that language for describing the relative orientations of 2 substituents on a benzene ring. And when we come back, I'll tell you which of these is the fastest. They do not all occur at equal rates. There's a very decided preference for which of these 3 types of products is going to form. All right, that's our lecture for today. So get out of here and go memorize the mechanisms for these 5 different classes of electrophilic aromatic substitution reactions. Get on the sapling problem sets and work as many problems as you can get your hands on. Go into the textbook and work every problem that you can get your hands on. Our exams will consist of problems you have never seen before. And the only way you're going to learn how to work problems you've never seen before is to get lots of practice. Okay, go do it and stay healthy and stay safe and sane. And keep going to discussion sections and office hours. Talk to you later.